Dynamic languages. I'm Greg Sullivan, your moderator today, and this is actually part of a course that myself, Jonathan Bachrach, and Kostas Arkoudis are teaching a graduate seminar on dynamic languages. And later, when we get to questions, we'll give preferences to students in that class, but everybody will be invited. Also, this is being webcast and recorded. And you can find out the recordings and also more information about our group and upcoming seminars and so forth at our website under the AI Lab webpage /projects/dynamic languages. Let's see. The first half, or slightly more than half of this hour-and-a-half panel, will be sort of scripted questions and answers with the panelists. The questions are very broad. You've seen them already on the announcement. And we'll just do a round-robin style from panelist to panelist. Each will have like 2 to 3 minutes per question. And then the last half hour or so, we'll open it up to general questions. All right, first I'll give you some quick bios of the people here. Will Klinger has been at Indiana University, Textronics, Light Chip Software, University of Oregon, and now is at Northeastern University, and also spending a sabbatical year at Sun Microsystems that he's just finishing up. In the Java Technology Research Group, he's written compilers for Max Scheme and Larceny, and proved cogeneration algorithm for Max Scheme correct. And lately he's been doing research on garbage collection. Next down is Dave Detlefs, Senior Staff Engineer, Java Topics Group at Sun Labs. He got his bachelor's at MIT, worked at TRW, then a staff programmer here at MIT at LCS, and then got his PhD from Carnegie Mellon in 1990. Then he's with DEX Systems Research Center, doing garbage collection and program verification, and then has been at Sun since 1996. He's working on JVM implementations, including garbage collection, JITs, and synchronization. Next, we have Matt Hostetter, was a member of the original LCS curl project, and then a co-founder of Curl Corporation and architect of the compiler team. Matt has a responsibility for various pieces of the curl runtime, and before curl, Matt implemented dynamically compiling CPU emulators, emulating various machines, including the Apple II and a Mac. And last is Martin Renard. Did his undergraduate at Brown and his PhD at Stanford. In between, worked at 2 startups, one doing electronic publishing, the other doing computer-aided drug design. He wrote the first self-debugger when he was in Dave Ungar's OO class, and has written a bunch of papers and has done mostly work on static analysis, in particular pointer and escape analysis, focusing on multi-threaded programs. All right, so again, the questions are a bit general, and we've asked the panelists to produce some specifics and to try to tie the answers in with compilation of dynamic languages. And we'll start with Will, and the question is, what is your guiding philosophy?
Okay. My guiding philosophy is that nothing I say has anything to do with the opinions of my employers. Technically, though, my guiding philosophy is that humans are stupid. To succeed at any cognitive task, we have to rely on abstraction. The purpose of abstraction is to simplify things so our limited brain power will have some chance of success. Abstractions are judged by how well they simplify. So I seek simplicity through abstraction. That's not to say that I like simple abstractions. Overly simple abstractions, such as thread models of concurrency, are often quite complex in use. What I am saying is that I like abstractions that make thinking simpler. That's enough metaphysical rant. Now I'm going to rant about compilers. We used to think, when we wrote a program, that we were programming the hardware. We also thought software was much easier to design and to change than hardware. Compilers were developed to make software easier to write. At that, they succeeded. But the compilers did something even more important. They decoupled software from hardware. This decoupling had several consequences. One is that programming languages developed as a kind of abstraction of the hardware. These programming language abstractions eventually became more important than the hardware itself. This turned the software-hardware dichotomy upside down. For several decades now, it has been easier to change the hardware than the software. I'm not saying it was easier to design, but to change the hardware than the software. On the hardware side, this was tremendously liberating and led to spectacular progress. On the software side, it has been a bit stultifying because it led to too much standardization of substandard programming languages, operating systems, and application programs. I wanted to end on a negative note. David?
I think Will's been working with me a lot recently. That's one reason why he believes in the stupidity of programmers. So I agree with a lot of what Will said. Our purpose in the universe as programming language implementers is to make it easier to write software by providing nice implementations of high-level languages so that people can do the interesting things that software allows us to do more easily. And obviously we want to take as many of the details of producing good software out of the programmer's domain. They shouldn't have to, like register allocation, you don't worry about putting reg declarations even if you are programming in C anymore. GC versus malloc and free is a mostly solved problem. Inlining, you probably don't want to be specifying yourself. You want that to be handled automatically because you make those decisions wrong and your program changes. Even if you make them right, your program changes and they're wrong again. So that has to be handled by the system, and that's our job. So that's all motherhood, and no one will disagree with that so much. In this context, I'm going to say one more thing that will be slightly controversial, perhaps. In terms of language design, while I'm all in favor of dynamic features in language implementation, I'm not very much in favor of, quote, dynamic features in language design. I think it's people often espouse such things for what I view as somewhat immature reasons, related to the amount of typing they have to do. And typing is a negligible fraction of getting a real program to work, obviously. So the more information you can put in your program and the more redundant it is with other information and the more checking you can have done statically and automatically, the better, I think, in getting programs to actually work. Consider civil engineering. If you were to go over that bridge they're building downtown without having it been simulated within an inch of its life, you wouldn't be very confident. Why do we allow the same thing to go on with software? I hope we don't in the future.
So let me tell you a little bit about the philosophy behind the curl language, because probably more of you have heard of Java than curl. We started as an MIT research project, and our goal was to integrate code and content, and also to have a gradual learning curve from the simple sort of markup style HTML level all the way up to full object-oriented programming, but all in one system and one language, where you can continue to use what you knew before, and it still works even at the higher levels. So in order to satisfy both ends of the spectrum, we made a few decisions in our language. You don't have to put in types in curl if you don't want to. If you're someone who's never even heard of a type, like my mother putting together a web page, she doesn't have to. Her program will run. It'll run more slowly and gets less checking. But I agree entirely with what Dave said about the need to have strong checking. So curl also has the possibility for full, strong type checking and more. And so that trying to satisfy those two different types of users has been a real challenge for us, but it also, I think, is a strength. Another part of our philosophy is we decided early on that we wanted curl to be compiled directly from source code. We think one of the reasons HTML has been successful is that you can just sit down and look at an HTML page and see how it's put together, copy the parts you want into your own page, and use it. Without having to go through any complicated compilation steps or use any other tools, you just click reload in your browser. Curl has that same flavor because we want to have that same kind of success. Microsoft claimed that one distinction between their IL, sort of their virtual machine, and a Java virtual machine is that their IL was designed to be JIT compiled from the beginning, and the Java virtual machine was designed to be interpreted, although of course they've had a lot of success JIT compiling it since then. Curl was really just designed to be compiled from source code in the very beginning, which has allowed us to have some kinds of higher level language constructs that you can't express in a more fixed bytecode, such as various kinds of looping constructs that avoid bounds checking in arrays. We know at a high level we can prove they're safe and don't have any security holes, but it'd be very hard if you broke it down all its little pieces to recover that information. Another part of our philosophy is that compile time and runtime are blurring together. Back when I was a student, we'd always talk about, well, you push everything to compile time that you can so that less happens at runtime. Our system just bounces back and forth between the two all the time. You can generate code on the fly and compile it. You can have arbitrary macros that transform source code to source code while your program is running, whatever you want. I think the distinction between compile and runtime has been artificial and has had a cost. One other piece of our philosophy is that curl is written in itself. We decided from the beginning that we want to eat our own dog food, so to speak, and that's actually had a big impact on our language design. That's one of the reasons we have as many features to turn on compile time type checking in our languages, because we had to use it ourselves for a long time. And so we found all the problems and annoyances and hopefully have ironed them out. And the last piece of our philosophy is that we want to have an extensible syntax so that users would be able to add to the language themselves. And I'll talk more about that later.
So let me preface my remarks by saying that these are geared mainly towards my research philosophy. If I was out in industry doing things, I might have a different philosophy. So the guiding philosophy behind my research is that you look at languages and you see that there is a general mechanism for doing pretty much anything you want to do. You need some memory? Fine. Allocate it on your garbage collected heap. You want to run your program? Great. Execute it sequentially. All this kind of stuff. Now, one style of research is to say, well, let's take these general purpose mechanisms and make them as efficient as we possibly can. Let's compile this sequential program down into really tight machine code. Let's build these really fantastic garbage collectors that go off and scan the heap unbelievably fast. Okay, this is not my style of research. My guiding philosophy is that there's no program in the world that really needs all the generality of these mechanisms. And in fact, if you look at any program, you'll find there's certain properties that program has. And if you can only find out those properties, you can take out these inefficient general purpose mechanisms with really efficient tailored mechanisms. And the guiding philosophy is there's always some way to find those properties out. Okay? So maybe you have to dynamically instrument the program and find out what's going on and get some idea of what they are. Maybe you need to go off and statically analyze the program for a couple of hours to figure out what's going on. But the guiding philosophy here is that you want to make the program run faster and do better things for the programmer by finding out the specific properties of the program you have at hand and exploiting those properties. And the philosophy is that it's always possible to do that.
All right. Next go around, I'll sort of march through.
Wait. I want to say one more thing. So Will talked about stupid programmers, and I kind of agree with him if you're a couple of months before the deadline. But my experience is that the closer to the deadline you get, the smarter they get, to the point where a couple of hours before the deadline, they are unbelievably smart. And the bottom line is your language had better be able to get out of the way of those unbelievably smart programmers then, or it's not going to be accepted by people because it won't satisfy their needs and won't allow them to get the job done when it really matters.
We'll start with Dave for the next one. So keep in mind this is a part related to a seminar for graduate students, so we're looking for these things that aren't solved also. So, and the question is, what do you see as the interesting open problems and future directions, particularly with respect to programming languages and so forth?
I'll mention two. The first one is dynamic compilation. With Java, we have the widespread adoption of a system where, for historical reasons mostly, the model was you're going to download some set of class files, essentially isomorphic representations of the source code, and then execute them. And the original model was going to be interpretation, and that's not fast enough, so people started making JIT compilers, just-in-time, aka dynamic compilers. So the first JIT compilers weren't competitive, say, with compiling the corresponding C program, the analogous C program offline, and gradually we've been sneaking up on that. The research question is, can you, in a dynamic compilation system, get the code quality of offline compilation without excessive overhead? Compilation times similar to the offline compilation times invoked at runtime, which is pretty much unacceptable. That's an interesting question. I'm hoping the answer is yes, because of a combination of compiling most of the code quickly with a very fast medium code quality compiler and then concentrating a highly optimizing compiler on a few hot methods. And there's some hope that that will yield a best of all world system, and that's still a very interesting research question. The second thing related to that, this is point 1 subpoint B, is can you do dynamic measurements of the system while it's running in some initial or continuously that will allow you to use this dynamic compilation infrastructure to recompile, optimizing for the actual code paths taken, other observed behaviors, and achieve results much better than offline compilation without the dynamic information. So that's a very interesting research question. Somewhat related to that, the second top-level thing, you go anywhere and there's this motherhood section of a lot of people's talks saying, oh, well, processors are getting faster, and memories are getting bigger, but the parts of memory you can actually get to, the caches in reasonable time, aren't getting any larger, relatively speaking. So obviously cache utilization is important. With languages like Java and other languages where you're insulated as a programmer from being able to ask questions about the actual physical layout of objects in memory, that insulation allows the system to transparently reorder fields and objects, break objects in two, move objects to enhance their locality. So I think a really interesting question over the next few years is, will we be able to do dynamic measurements that allow us to do all those sorts of restructurings in order to enhance cache locality and thus cache speed? So, sorry, over.
Yeah, I agree with those concerns. One specific issue that we're having to address, because curl is compiled from source code down to machine code on the fly, we have a little more overhead than like the Java virtual machine and similar systems. So for us, we're trying to find ways to reduce that overhead as far as we can. What we've done so far is we've pushed lazy compilation to the point where we don't even look at things that we're not going to use, but we still have a little bit more work to do there. For example, you can imagine if the user defines a class, it would be nice to parse nothing about that class except its name until someone needs a little more information. Maybe when someone needs to know a field, you just process the minimal amount of information you need to find out where that field is in the object, but don't do anything else. When they actually go to create the object, then maybe you compile a little bit more and a little bit more and so on. That model is very different than the traditional compiler model where you just have several separate passes you make to the program and then you're done. This is a lot more sort of lazy dependency graph-oriented approach. So that's a big challenge for us. Another interesting example, if you look at like parameterized types, they're pretty good, like C++ templates, the fact they let you write code that you can specialize to different purposes. I mean, the syntax may not be what you want, but the idea is good. But it's not quite general enough. A guy at curl the other day wanted to have a parameterized type, and he wanted one method to be completely different if its argument was something else. Well, we don't have a way to express that now. But it seems like that'd be a natural extension of letting programmers do what it is they want to do, giving a little more flexibility how they design their class. That's sort of a language design challenge for us. And one other thing that I'm going to be interested to see how it plays out is with this trade-off between compilation time and runtime, one of the sort of obvious trade-offs you can make is to say, well, we'll compile things offline. When you go to bed at night, we'll sit there and optimize the code that you downloaded that day so tomorrow it's faster. I'm not sure if that's going to win out or if people are just going to make their compilers faster and faster over time so that sort of complexity isn't necessary. That's something else we're going to explore.
Okay. All right. So here's what I think. Programming is a human activity, and for the purposes of this discussion, there's two kinds of people. There's people who like to experience life. They want to press the button and see what happens. Good, bad, indifferent, they just want to see what happens. Then there are people who want to plan. They want to think about the future, predict what's going to happen, set things up so that it all works out, and then, hit the domino at one end and watch all the dominoes fall down all over the table in the precise order that they have planned out. Now, the great thing about dynamic programming environments is that they let you change things dynamically. They let you say, I don't like the way things are going right now. I want to reload some different part of the system with a changed implementation. But the problem is, the current environments that you can get like this, they don't support either of the two kinds of people very well. Here's what happens if you're an experiencer. You say, I think it would be a cool thing to do to, replace the implementation of vectors internally with linked lists and see what happens. Okay? So you go away and hack for 10 minutes and push the button, and boom, there it is. All of a sudden, all of your vectors are linked lists now. But you don't get the full experience because the system isn't designed to let you see what's happening. What happens is, maybe some part of it runs really slowly, maybe some part of it, takes a lot of garbage collection time where it didn't before, but you really can't figure out what's going on in the system. So let's say you're a planner. You get the idea. You say it might be a good idea to replace all my implementations of vectors with linked lists internal. But now you want to know, what's going to happen if I do this? Well, you'd like to be able to peer into the system transparently, see all the places that you use vectors, understand the context in which they're used, understand the performance, the implicit performance expectations that clients have of them, understand how they're interacting with the garbage collector, understand what happens to vectors as you run the program. And again, there's little support for this. You've got to do a lot of typing in your debugger to find out this kind of information. So what we really need is a system where you've got the internal structure of the system and what's going on in it designed to be exposed visually at a very high bandwidth to the person using the system. It would be really helpful to both kinds of people, because then when the experiencers go in and hack the system, they get a much better experience because there's a whole lot more stuff going on that they can see and understand. The planners are going to have a much better time because they have a much richer planning experience. They get to sit down there and think about all the wonderful things that will happen if they do this hack. Okay? So I think a more open system where you could see what's going on in the objects. I think the early Smalltalk systems did this very well, or at least much better than current systems do, because there you could, say, I could say, what's this object look like? Boom, and it flashed the object up on you. You could click on the links and you get this big chain of objects on your screen, and it was much more open than a lot of systems are. I think there's a couple of reasons why systems have tended not to be as open as they might otherwise be. One is that you've got heavy-duty compilers out there morphing the code beyond recognition so it'll execute efficiently, which is a great goal. But it makes it difficult to reverse all those steps of compilation and expose the abstraction back to the guy who's using the system. And a second reason is that people have taken abstraction too seriously. They've taken abstraction to believe that it's always right to hide what's going on behind this little curtain. But I don't think that's true if you're looking at the behavior of a system and trying to figure out what's going on. There you want to be able to see everything. Okay, so that's one future direction. How do you make these systems open while preserving all the good things they do for us? The second future direction, I think, is that people are going to replace type systems. You're no longer going to have typed languages anymore. What you're going to have is you're going to have a dynamically typed language, a dynamically safe language with a bunch of stuff on the side that tells you what's going on. So now instead of having just a single type language you can use to express your expectations of what the program is doing, you can have general purpose assertions, general purpose properties, and you'll have very powerful mechanisms to come in, very powerful analyzers that go in and verify that your assertions are correct. So I think you'll see much more powerful languages replacing type systems, and type systems moving, and their more powerful successors moving away from the core language into meta languages and things that are separated from the program both conceptually and textually.
Okay, well, what I think the world of dynamic languages needs more than anything else is a runtime system that supports dynamic languages well and runs on all major hardware platforms. This is technically feasible, but we don't have it, and I'm really not optimistic we're going to get it anytime soon. The previous panel discussion was about runtime. Did anyone here notice that no one even mentioned the Java virtual machine or Microsoft's .NET Common Language Runtime at a discussion on runtime? The Java virtual machine was designed to run Java, and it doesn't support other dynamic languages at all well. Microsoft's .NET runtime might be slightly better in that respect. After all, it has to support C++, C#, Visual Basic, some other things.
Haskell.
Who knows? Whoa, whoa! Okay, well, so maybe it's better, but I doubt whether Microsoft is going to push all that hard to make the .NET Common Language runtime universally available on non-Microsoft platforms. So right now, C++, for a compiler writer, C++ might be the best portable target for dynamic languages in general. And it isn't a full runtime system. It's basically a portable optimizing assembler, whose most attractive feature is that it isn't actively hostile to things like proper tail recursion and garbage collection. So why do I think a portable runtime is so important? It's because the world of dynamic languages is still a small one. We can't afford to squander all of our energy building separate back-ends and runtime systems for every language and for every platform. We also need to reduce the volume of trusted code, and a portable runtime helps with that. It doesn't solve the problem, but it helps. Here I think we need to distinguish safety properties from correctness. There's been a lot of work in recent years on verifying some safety properties at runtime or load time. For example, the bytecode verifier in Java or typed assembly language, things like that. But if you're concerned about correctness, not just safety properties, you really have to do something about the entire path. You need a trusted path all the way from source code to machine code. And to minimize the volume of trusted code with respect to correctness, that's, I think, a major research area.
All right, our third question is asking the assembled wizards, what little-known secrets would you like to share with the audience? This would be, how do you get the computers of the languages to perform their magic? What's behind the scenes? And we'll start with Matt.
Okay. One thing which wasn't obvious to me when I started working on compilers was that just how effective even lame optimizations can be. You can take a compiler for a language and just do the simplest thing, maybe a little constant folding and a very trivial register allocator. You do your job right, you'll be 2/3 as fast as a good C compiler. And for a lot of jobs, that's good enough. And there's no need to go off and do a lot of fancy optimizations. Another thing I found surprising was that these days, JITs can often generate better code than the static compilers, because the JITs have a lot of access to dynamic information that static compilers didn't. They know how to reorder things. As Dave mentioned, you can reorder fields even potentially dynamically. Inline things that get called a lot. These are all things you can't do offline. Some people have done these profile-directed feedback systems for static compilers, where you run the program, collect some information, and then recompile the program using that. But that still doesn't help you if the behavior of a program depends a lot on the data, whereas the JIT system can always adapt to whatever is actually happening right now with the program. So I think that's really interesting. Another thing that you shouldn't be afraid to do if you're writing a compiler is just write a translator from your language to C when you're getting started. Our system still uses that to bootstrap ourselves, and it's useful if you want to port to a new platform. There's no need to just get started right away with a full JIT. Now, if your language is really dynamic, that may restrict what features your compiler can use, but usually you can use enough of a subset that a C translator will work. Another thing that you should pay attention to is use domain-specific languages wherever you can when writing your compiler. Lex and Yak have been very popular, not just because someone else wrote them and they work, but because they let you express really complex ideas concisely. In the various projects I've done, the first thing I've done is I've sat down and just written up a file describing, the architecture I'm working with. The 68K emulator I wrote a big description of the architecture and used that to machine generate a sort of interpreter for the processor. Later on, I got more aggressive and modified my translator to actually produce a compiler that created x86 code. And that was possible because there was this domain-specific language encoding the semantics in one place. Definitely a big win to do that.
So I really don't have any little-known secrets. If I had any, I'd publish them and make them well-known pearls of wisdom or whatever they were. So I guess as close as it comes is just my general philosophy of, it's always possible to figure out what you want to know about a program if you know it's true, sort of intuitively at the high level, at the programmer level. And you can automate that process more often than you think. So take it away, Rob.
Well, I came up with 4 little-known secrets. Maybe some of them are wider known than others. The first one is the usefulness of the PowerPC's RLWINM instruction. Rotate leftward, immediate, then and with mask. I'm
You
not
think
gonna
he's
say-
kidding?
I am not kidding, but I'm not going to say anything more about that one. The second one is the synergy between proper tail recursion, optimization of leaf procedures, and frame optimization. In properly tail recursive compilers, the number of leaf procedures, whether you reckon statically or dynamically, goes way up, and the number of stack frames that you allocate can go way down. The functional world knows this, but the object-oriented world hasn't really caught on yet. Number 3, the synergy between program transformations and flow analysis. Flow analysis becomes more useful when combined with program transformations that rewrite the program into a more easily analyzed form. And so they contribute to each other in a very interesting way. Things like inlining, lambda lifting, splitting of polymorphic procedures into monomorphic procedures, things like that. So there's a real synergy there, and it's amazing how much that buys you when you really start to look at it. And number 4, why generational garbage collection is a win. Not that it is a win, but why it is a win. You often hear that most objects die young. That's true, but irrelevant. When general garbage collection is a win, it's because there are lots of objects that die young and lots of objects that don't. You can waste a lot of time by looking at those long-lived objects on every collection. The tenure process is a very inexpensive way to isolate and then to ignore long-lived objects. David.
I want to echo some previous comments. Well, one thing that surprised me when I started working on Java, our group was trying to do research in Java garbage collection. So we had an existing product that we were trying to do this research in, and we discovered that garbage collection wasn't a problem because it had an interpreter only at that time, and the denominator was so large that it didn't matter what we did about garbage collection. It was a negligible fraction. So we started working on decreasing the denominator so that making GC a problem so we could work on it. So we inherited a JIT compiler from the product group that was what we'll call a template-based JIT compiler. You know, you have your bytecode program, and the compiler consists of a big loop for each bytecode instruction, do a big switch statement for the bytecode, and emit some code for that instruction. So we hacked on this for a couple years, and much as Matt said, it's amazing how close you can get to high-quality code on a very low cycles per bytecode budget. You know, this sort of there's no intermediate language here. There's 2 passes, and then one pass to do a little bit of analysis, another pass to generate code. You can do kind of online versions of your favorite optimizations and be surprisingly effective. I mean, we did. Where's the list? Kind of round-robin probabilistic register allocation, and that worked out pretty well, at least on a register-rich architecture like the Spark, where almost anything will work out, in fairness. Common sub-expression elimination, constant propagation. Even went as far, I did like 6 months of work where I analyzed innermost loops to do array bounds check elimination, even including hoisting a predicate that you could test outside the loop, and if it's true, you can eliminate the bounds check within a loop. Otherwise, you execute an unoptimized version of the array. All of this was accomplished in a compiler so we had that compiler, we had another compiler which was an adaptation of a traditional compiler to be a JIT. And the factor in compilation speed was something on the order of between 10 and 100, figure 30. So we can get within 2/3 of the performance at 1/30th of the cost. So that's really surprising. It means that it's never worthwhile to interpret more than a negligible fraction of the time, because it's so cheap to do if you can have a compiler like this, you can have almost all the code you actually execute be at least compiled to that level. Though it is still occasionally useful to interpret at least a couple executions of a method in the Java case, because then you can do all the symbol resolution that you have to do, that the language says you have to wait and do it when you first encounter it. So you get a little bit of information to guide that first compilation, and then if you want, you can do that first compilation to gather more information to guide a later optimizing compilation if that turns out to be a hot method. So that was surprising to me, and I think it's not often appreciated. Thank you.
Okay, the next question is, keep in mind that the context here is both a graduate course and also the AI lab, where there's a sort of long history of dynamic languages that never quite caught on. And the question is, the question is, what good ideas have been dropped but whose time has come? And we'll start with Martin.
Okay, so the first set of good ideas whose time has come is driven by the fact that computers are moving out into the physical world and interacting with the physical world more and more and more and more, which means that the effects they have on the objects they compute with and affect are more and more difficult to reverse, which means that you care more and more about the correctness of your program and what it does. So there's a couple of ways to attack this problem. One way is to say, well, I really care about this. In fact, I'm going to engineer my system, and I can state my requirements pretty carefully, and I can translate those requirements down into properties that my program has to satisfy. I'm going to prove that my program has these properties. Okay, so I think there's room here for what most people think of as a bad idea, namely full program verification. It'll be real interesting to see how close we come to that over the next 10, 20 years, because you'll notice that there's been a lot of emphasis recently on formal methods, and people are starting to prove more and more and more sophisticated properties of programs. But people, I still think, view full program verification being as comfortably out of range. And I think that may change for some small class of programs that interact intimately with the physical world. Another question is, another way of getting there is to say, well, okay, I don't necessarily want to verify my program, but my program is simple enough so that I can just basically simulate everything it could possibly do, i.e. use model checking. So I can write down a couple of properties and sit there and let the computer run and run and run and run and run and explore the state space at some suitable level of abstraction and see what will happen. This has been very successful in the hardware end of things, and I think there's a chance that it'll be very successful in the software end of things. So, but let's say that neither of these two technologies works out. Well, there's a third technology. That is, and you have to believe the reason these first two technologies aren't going to work out is because people are going to find it very difficult to express what they want their program to do. So this means that if these two technologies don't work out, and you need a reliable piece of software, you have to rely on something else to tell you the properties that the program should have. Okay, so well, that's an artificial intelligence program, right? So you have to have an automatic programming system that will go in and make all the assumptions about the world and have all the knowledge about the world that you can't get people to tell you. Well, we'll see if that works out. That'll be an interesting scenario. And finally, if you don't believe in any of these, the alternative is just to sit down and let people do it themselves the way they've been doing it for all these years. And I think whether that's acceptable to people or not is going to be less of a technical question than a social and legal question. I think if you can show that there's an alternative that you can deploy that would prevent accidents, it's going to be very difficult for people to defend in court software that wasn't developed using those methodologies or tools. And I think that's going to be it's possible that that's the one thing that will drive people towards developing these kind of software in more reliable ways. Okay, so that's one idea. So here's another idea whose time sort of has already come, but I'd just like to re-emphasize it. Higher level programming languages, things like Perl. You know, Perl is a great language if what you want to do is hack a bunch of text strings in a file. Back in the 70s, there was this language called SetL, where you didn't program with integers and arrays and things like that. You programmed with sets and relations, which was very nice. And I think the standard relationship that you have between objects right now is a reference from one object to the other. And I think the reason you have that relationship is because it's very easy to implement that relationship using a single word pointer on a machine. And I think the time is right to start looking for for richer relationships between objects built into languages, and not worry as much about the implementation cost that having those features might entail. I guess some ideas whose time's come and gone and should stay gone. Dynamic inheritance. You guys, so you guys remember dynamic inheritance? So dynamic inheritance is a concept that, hey, I'm a class A right now, but maybe later on the same object needs to be a class B. And you look at the code, and you can do some unbelievably cool things with this, right? Your object at the front of the list behaves differently from all the objects in the middle of the list, behaves differently from the objects at the end of the list, and you type 3 lines of code, and you're doing some really cool, complicated thing. But it turns out that you just can't deal with the complexity of this when you build big systems, or even medium-sized systems, or even, quite frankly, small systems. So that's a cool idea whose time, I think, has come and gone, and it's going to be gone for a while. And I'd even generalize this to multiple inheritance, and perhaps even arguably single inheritance. Because here, because you can view single inheritance as something that you ought to do not at compile time, not at runtime, but at when you're typing in the editor. So this is an idea that kind of comes and goes, and it'll be interesting to see whether people like that way of programming or not. But anyway, I guess I've said enough, so I guess you're up, Will.
Okay. A good idea that's been dropped but whose time has now come, uncall, a universal compiler-oriented language. That's the portable runtime system I was talking about earlier that we need. Beyond that, I found it easier to list bad ideas like Martin that haven't been dropped but whose time is nonetheless passed. Finalizers, for instance. On Sunday night, a friend was telling me that C++ was much better than Java for his application because he couldn't predict when a Java finalizer would run. I asked him, why don't you just call a pseudo destructor method explicitly whenever the relevant object goes out of scope? He said it's hairy in the presence of exceptions, and some programmer is bound to get it wrong or forget to do it at all. Okay, why not make it impossible to create these objects except by using a macro that generates the finalization code automatically? He said Java doesn't have macros. He had a point. I think programming language designers have been avoiding macros because they hate C macros. Well, C macros ought to be hated, but designers have drawn the wrong conclusion from their badness. As bad as they are, programmers use them. Why? Because they serve a purpose. Language designers should not be so arrogant as to think that their language is so much better than C that no project will ever need a syntactic abstraction that the designer failed to anticipate. Hygienic macros are a major win. So that's the good idea. Another bad idea, explicit deallocation. The good idea, garbage collection, is no longer controversial, so I won't say anything more about it. Another bad idea, threads, by which I mean the abstraction that views computation as a small army of creatures hammering away on a monolithic shared memory. To keep them from hammering each other's thumbs, you mentally carve that monolithic memory into shared pieces that require synchronization and unshared pieces that don't. Why not use that mental carving as the fundamental abstraction? Why not make that abstraction explicit in the source program so the compiler and runtime system can enforce it? You'd get better compiler optimization that way too. Another bad idea, over-reliance on side effects. For example, the use of assignments to initialize objects. You shouldn't have to have a clever compiler to distinguish initialization of immutable instance variables from side effects to mutable variables. Const should be the default, and mutable should be the keyword that you have to use when you want to have side effects. Another bad idea, there are lots of them, signed arithmetic modulo some power of 2. Programmers just can't be relied upon to remember that half the laws of arithmetic don't hold. A good idea, whose time is nonetheless past, I think, whole program optimization. As has been discussed already, we're moving toward load time and dynamic optimization, and I think that's the way we'll be going in the future. David.
Okay. I got two possibilities. I have a hard time with this question, but there's partial evaluation, has a long heritage. In object-oriented languages, sometimes it's come up in the guise of specialization, where you have a method and you I think that technical term really means have a method where you get to assume that you know the actual dynamic type of this. But, so there's a lot of situations in which you might wish to augment call sites to note commonalities or common things in the calls to a method, and then optimize a version of the method so that it performs better for those common call patterns. For example, we talked about knowing the dynamic type of the receiver or perhaps the arguments. This would help in optimizing further method dispatch within the called method, or instance of, or casts, for example. Imagine a situation where a method takes two array arguments and then it's going to loop over them both simultaneously. You might wish to note that it's almost always the case that those two arrays are of equal length in order to perhaps get rid of the bounds checks. So there's a lot of interesting things like that that could be done. The challenge there is identifying the common patterns, the ones that could be properly optimized for without introducing excessive overhead. Another idea not in compilation that's been kind of discarded, which might be coming around again, is reference counting garbage collection. With Java and the use of if Java is a dynamic language, here we have the first use of garbage collected language anyway for large business-oriented applications. We talk to customers all the time who say, well, we're going to run our program with, like, say, 10 gigabytes of live data. Is that okay? And, you know, what can they do with 10 gigabytes of live data? Well, and we asked them, and it turns out that 9.7 gigabytes of those is in-memory caches of some big database that's changing on timescales of weeks or months. So we have a big heap, but it's very nearly static. So the garbage collection algorithms we've been working on aren't optimized for that case, a very large, mostly static heap. So reference counting they always still have to trace the whole heap once in a while, and you know, as 10 gigabytes becomes 100, that becomes a little bit dicey. Reference counting has the nice feature that you only concerned with, usually anyway, the objects that are actually accessed, whose reference pattern changes. So, you know, it's a little bit heretical, but maybe that sort of idea is coming back. And there's been a few papers on stuff like that in PLDI and OOPSLA recently.
So I just want to say I agree strongly with Will's claims about that powerful macros are really the way to go in the future. I mentioned earlier that I think compile time and runtime are blurring together. I think the next thing that we should see is that the language and the library should begin to blur together a little bit too. We've set up a macro system, which unfortunately we're not proud of enough yet to make public, which allows you to do arbitrary transformations of source code objects to source code objects at runtime. Not just a template-based thing, but you can actually examine the source code and do any analysis you want, call whatever procedures you want. We've used that in, for example, our graphics system to add some forms which are tailored to the needs of graphics programmers. For example, we have a 4-pixel form that lets you iterate through all the pixels in a pix map and doing some operation to each pixel. This code that's generated is extremely efficient and get rid of all the array bounds checkings, but also we don't guarantee what order it happens in when we also allow it to happen in parallel. If you have 2 CPUs processing the image, the compiler is free to launch half on each CPU. That kind of extension for these domain-specific things is really what's going to make languages a lot more powerful in the future, I think. Another good idea whose time has come and is integrating documentation with your code. JavaDoc does this, and we've adopted something similar for our code. It's clearly the right thing to keep the code and the information about it together. If you look at a current system like a C program, you'll see there's comments in the headers, comments in the C code, some documentation separately, and all three of those things have to be tracked in sync, and that's just silly. The next good idea, I think, whose time has come is using good compiler IRs even in JITs. People's intuition used to be that if you can sit down and make a JIT, you just don't have enough time to do all the really classic full optimizations, and you have to keep things simple and small so it can complete in time. That used to be true, but with computers doubling in speed every 18 months or so, the fraction of time that you spend actually doing the compilation is getting small and small enough that you can afford to use these nice IRs, and I suggest you do that from the beginning. My personal opinion on this is that SSA is the way to go. My understanding that's what Sun's using in their hotspot JIT with a lot of success. And one other good idea as time has come that I mentioned earlier is aggressive compilation directly from source code. There's just a lot of advantages to doing that way, and you keep a lot of flexibility for yourself for the future.
Can I react a little bit? Threads. I think what Will says about threads is absolutely true now. It's almost unbelievably hard to keep your head on straight if you don't have a way of knowing that the data that you're accessing without synchronization is not accessible to other threads. However, I think people are developing type systems and that kind of automated reasoning systems that lets you take this kind of, lets you explicitly separate this kind of data. And I think when that happens, it's going to become much easier to program using threads, and people are going to start resonating more with the power that threads gives you. Second, whole program analysis. I think it's absolutely true. It's very difficult to do a whole program analysis or optimization across a large program, but notice that every time you compile a program that has a statically typed, that has a static type system, you're doing some form of whole program analysis. It's just that you're leveraging assertions at procedure boundaries that let you do that. And I think that kind of whole program analysis will become more common. And one last thing, a bad idea whose time has come, okay? So it used to be back in the early days of programming languages, you'd go into your programming languages class and they'd teach you about the go-to statement. They'd say, you know, here's how you write the go-to statement. You say, if condition go-to label foo, okay? And you understood this. And then people used to, late at night, think of cool variations of this. And one of the cool variations of this was the conditional come from statement. So what you'd do is you'd go down to the end of your program and you'd write, if some condition, then come from, you know, label 40 right here. And what that meant was whenever control reached label 40, you'd evaluate the condition. And if it evaluated to true, you'd immediately jump to the code down at the bottom of the program. And everybody said, oh, this is ridiculous. This is totally unusable. But it turns out that there's this thing called aspect-oriented programming. And what aspect-oriented programming is, and you should go out and read the papers, it's a structured, disciplined way of using the conditional come-from operation. And that's a bad idea whose time has come.
Okay, the final question overlaps especially with the final panel that on May 10th, which is about language design, and also reiterate some of the earlier questions. And we'll start with Will. It's what are some pitfalls, gotchas for language design and implementation?
Well, one classic pitfall is to assume that a sufficiently clever compiler can compensate for poor design of a programming language or target architecture. I think I just heard a variation of it by assuming that a sufficiently clever verification system would compensate for a problem in a programming language. Another classic pitfall, though, is to assume that compilers are stupid. Some target architectures do things at runtime that ought to have been done at compile time or link time. Some programming languages are intended to give programmers the power to write more efficient code, but in reality require a very clever compiler to clean up after all the incorrect guesses that programmers make about what's efficient and what isn't. Let's see, more pitfalls. Slow code doesn't fly. Slow compilers aren't appreciated. Just-in-time compilers can't do heavy-duty optimization. So, translating source code into reasonably efficient machine code has to be straightforward. If it isn't, there's something wrong, either with the design of the language or with the design of the target architecture. If you're implementing a runtime system for dynamic language X, and language Y is the language du jour of industry, don't assume that it is enough to support languages X and Y. In reality, the dynamic language X won't matter at all, in which case why bother, or else it will succeed, in which case software developers will want to use it in combination with all manner of other languages, including other dynamic languages.
Pitfalls. So working on Java, I'm a researcher by temperament and by previous experience. In Java, I'm in a research group, but one that works very closely with product groups. And the scale of the Java phenomenon is unprecedented in my experience. Well, that's not huge experience, but when something is as widespread as Java, you can't optimize for the common case. You can't over-optimize for the common case because it's so widespread that the uncommon cases are important too. And you want to especially avoid optimizations that, while they benefit the common case, they penalize the uncommon case. For example, I'm not sure this is a great example, but there's the Java language has the somewhat unusual design decision that each object is potentially lockable. That the lock operation is a method on object, the root of the class hierarchy. So it's assumed that most objects aren't locked, but when they are, you have to support it. So that's an interesting implementation thing. When there's a lot of implementations of Java locking, most of them are of the form, make assumptions that most objects are never locked. Those that are seldom contended for. That it's seldom that objects are almost always unlocked when you attempt to lock them. So most of them, when contention happens, do some sort of what they call lock expansion. They allocate this other data structure that corresponds to the operating system mutex and associate it with the regular object in the first place. So for most programs this is true. If you have an occasional program, however, for which many objects are occasionally contended, this is going to be an inefficient strategy. So there's alternate strategies that don't have that drawback. So that's one example. You don't want to over-optimize for the common case. My other pet peeve is moving runtime functionality into the source language. It's often, there's sometimes the phrase above and below the line. Like, here's the virtual machine interface, and the source language is above it, and the virtual machine implementation is below it. And it's often stated that it's just an intrinsically good thing to move pieces of the what are ostensibly pieces of the virtual machine implementation out into the source language. For example, in Java, there's Java-lang reference. Weak reference and finalization processing is now largely done in the source language. And I was just talking with a product engineer like 20 minutes before I left here about some difficulties this has caused, because there's a lock at the source level that interacts with internal locks protecting internal data structures, and you have to get the locking order right to avoid deadlocks. And I just think it's insufficiently appreciated how much difficulty this sort of thing can cause. Another instance is allocating meta objects, for example, compiled code within the heap. This has many good things. You have a single shared resource of memory, and you're managing it uniformly. But it also causes a lot of problems when it's no longer the case that all allocations are explicit in the source code. Execution of a program may load a new class that will implicitly cause allocation, and there's interactions we didn't anticipate. Meta-circular compilers, where the compiler is written in itself. For a language like Java, you have to think, is this intrinsically good, or does it serve some purpose? If you already have a compiler that's written in a lower level language like C++, what benefit are you actually gaining? I just want to make sure people ask that question and answer it to their satisfaction, rather than just assuming that doing a language in itself is an intrinsic good thing.
So a few pitfalls I've noticed. One thing to watch out for in writing compilers is diminishing returns. Especially when you're in grad school and reading lots of papers, a lot of the papers tend to focus on things which are very quantitative and easy to analyze. And a lot of those problems just don't matter for most people. There's a lot of work done on big scientific matrix codes and things. But unless you expect scientists are going to be using your language, don't worry about it. Focus on something else. It's really easy to get stuck in the trap of throwing together a few benchmarks and just obsessing over those benchmarks, making them as fast as you can because it's fun. But that may not make your users the happiest. Another problem that every compiler I've ever seen has had is insufficient testing. I mean, I don't think I've ever used a compiler that didn't have some bugs in it. And that can be really bad, especially if you're working on a dynamic language. Compiler bugs can be security holes that people can exploit. You know, if you use the wrong register somewhere, well, suddenly maybe they can scribble on memory they're not supposed to see, and then bam, they can take over your machine and wipe your hard drive. But be very, very careful. So my advice here is to write just tons of automated tests for your compiler if you can. If you start out doing that early on, you'll be happier. You'll get your compiler done faster. And the second thing is just take every line of code you possibly can, just run it through your compiler in some automated way all the time. Even if you don't even run it, just compile it and hope that maybe it'll catch some asserts firing your compiler. An actual example of this sort of thing that happened to me was back when I was working on this Macintosh emulator. I was dynamically compiling a 68K program to x86. We were playing the game Prince of Persia, the Macintosh version, on my PC. And I was walking my little guy across the screen. I found that whenever I climbed up a certain ladder on a certain screen, the guy vanished. And I walked back, he was fine. It turns out, after a lot of debugging, that I'd gotten a particular case of a signed 16-bit write shift wrong. And everything about the whole system worked, except the guy disappeared on the ladder. And so that was a hole in my test suites. So it pays to cover all of your bases, or you'll spend a lot of frustrating time debugging. And the last thing I want to say is watch out for language constructs which look like they're efficient, but are actually incredibly slow. This has been a problem for us because we want to support both these naive users who aren't using types and telling the compiler anything, and also the efficient users. You can write 10 characters which might take 10,000 cycles to run, even though it looks like it'll take 5. What we've had to do there is allow you, if you're a sophisticated user, to tell the compiler, don't let me do these surprisingly slow things, make me say I meant to do it. But if you don't have even something like that, people are going to have a very hard time making their programs run efficiently because their intuitions may not line up with your implementation.
So first gotcha and pitfall here is gimmicky language features. I've mentioned one already, dynamic inheritance. There's also been a history of elaborate synchronization constructs, path expressions, things that describe all the operations you want to have happening on your objects at various different points in time. All these look very, very good when you start comparing them against a set of small examples. But when people are using them in a broader context, they tend to diminish in importance, complicate your implementation, and make life harder for everybody. The second gotcha, and this is especially for people doing research, focus carefully on what your research goals are and eliminate all other sources of complexity. Don't do, if you're not doing research on dynamic dispatch, don't build a system that supports dynamic dispatch. If you're not doing research on I don't know what, message sends to access primitive fields, right? Make life easier on yourself and just let people declare structs of objects with integers and things like that in them. Don't take your levels of abstraction so far down that you've got to do some optimizations just to get the basic efficiency back. But the other pitfall is don't go down a rat hole. A rat hole is when you want to get some result, you want to make some program run twice as fast. And you can feel that that you can make the program run twice as fast, but you don't know that you can make it run twice as fast. And you spend 6 months with the feeling that you're one day of hacking away from a factor of 2 in performance. Okay? Cut that off really quickly. Have some concrete evidence that you can accomplish your goal before you go off and invest a huge amount of time attempting to accomplish it.
Have an advisor with an advanced rat hole detection system.
Have an advisor who's gone down a few of them in the past himself.
Okay, so now we can open up for questions, preferably from students in our class, but also anyone else. Yep.
I just have one question. Part of your comments was about the title of dynamic inheritance.
Yeah.
It sounded like you sort of wanted to say objects can never change their behavior. I wanted to understand, is there a distinction you're making between objects that can change their behavior over time versus what you were calling dynamic inheritance?
So I think you put your finger on a very good point, and that is that objects play different roles at different points in the computation. They therefore have different behaviors at different points in the computation. And it's important that this be reflected in programs somehow. And one really cute way to do it is to use dynamic inheritance, right? Because you just swing the pointer. It's very attractive. I think the way you do this is you structure the control flow of your program so that you just don't invoke the bad operations on the object when it's in the wrong state. And it's suboptimal if you look at it from that particular perspective. But in the broader scheme of things, the fixed dynamic inheritance is worse than the cure, or at least that's, yeah.
Well, I was going to put this in the context of the systems that have to run continually. It sort of says, if I'll never be able to update this object, update the behavior of this object, other than by taking the whole system down and recompiling everything.
Well, you can download new code, can't you?
Excuse me?
You can download new code.
But how do I change that old object so that old object now runs the new code?
Well, you have some meta level in your system, right? That says, so hey, I'm changing things now, right? There's two levels. There's two levels in any system. One is the level that you're programming in when you're writing the code. The other is the level that you're operating at when you're managing the system and understanding its behavior. And I think if you're talking about very long-running systems where objects need to change their behavior over time, or you need to be able to change the way the system works, you're better off separating that into another level where you have somebody who can A, see beyond all the abstractions, B, see what's going on in the system and has tools that support that, and 3, do things that your programmer wouldn't be supported by the programming paradigm of your language that you're using. I think that's my opinion about the sane way to do it. So of course there's going to be a group of people who go off and say, wouldn't it be cool if we could mix these two metaphors and have a great language that does it? And maybe they'll go off and do some great research and find out a good way to support this kind of stuff. But I think right now I don't know how to do it in a way that I think keeps me sane or anybody else sane.
I want to echo that and amplify a little bit. We have there are those within Sun that argue that there are customers that have servers that are supposed to run the proverbial 24/7, and I sometimes hear 24/7 360, and I get a type error. I hate that. And the argument is that they need to be able to update code dynamically within the running Java program in order to fix bugs, and this makes me extremely nervous. I mean, if their method is wrong, the analysis you would have to do, there's a couple cases in which it makes sense, right? You have a pure function, and it was correct before, and you're introducing a new correct, more efficient implementation of that function. All right, that's fine. I understand that. But almost every other case, if there were side effects, trying to do the analysis to determine the scope of the errors that might have been left in the rest of the state of the currently running system because of the error in this method is just too daunting to me. I can't imagine us getting that right.
Well, I'm not saying that you're automatically going to do that, but right now because you can't change the program at all. I mean, I guess it's sort of saying, it's the usual thing to say, design the program and say, I'm going to leave this feature out because too many people are going to use it. That's sort of recommending some accuracy.
Let me give you another example. The FAA, bring down certain systems, they patch them as they're running. You don't have a choice, right? And lives depend on them.
Yeah.
So you can't not solve this problem.
Well, you could ground the planes for a little while or something.
No, you can't.
No, I think you're missing another important point, which is that there can be things that are functionally not working that don't actually leave long-lived bits of data around, and that arises a lot.
Fair enough. Trying to be controversial.
Okay. I'm just fighting back then.
I was actually thinking of us in the sort of the context of distributed systems where the object that you're calling to or whatever might be owned by somebody else, and so they may want to upgrade it, they may want to do something you don't necessarily control it locally. But so it comes down. I still may be making assumptions about what it does or its types or whatever like that, and so it seems like sort of a related issue of how to manage that kind of change.
So my initial reaction is there are people who criticize distributed object-oriented programming, basically citing the exact property that you've just mentioned. They say distributed objects tie things together very tightly in ways that makes it difficult to change the system because you've got references that go across machines that are, what do you do when you need to replace one object with another and you've got a reference to the old object. I think it's possible to preserve some of the attractive features of object-oriented programming, distributed object programming. But you have to take a look at how you pull back from the abstractions that have worked so well on single machines and allow people to do things like redirect references and do this kind of meta system futzing that you have to do in a distributed long-lived system.
Okay.
I don't know if that's addressing the issue you
Well,
raised it on.
let's move to some
Okay.
other.
I have two questions. One is that I'd like to hear more on how curl deals with mixed mode code, where some is manifestly typed and some isn't. And the other question I have is that David mentions that ref counting GC is coming back, and Will mentions that finalizers are a bad idea. Python uses ref counting GC to provide good semantics for finalizers, so I'm wondering if this is a good idea or a bad idea.
Let's start with Matt doing the mixed typing.
Okay. The way it works in curl is you can take your program and remove all the type declarations from your variables and fields, and they'll be replaced with a type called any, which is a lot like, say, a type in Lisp or other languages, where all the type information is carried around with that object at runtime. All the same operations work on any's as work on normal objects. For example, if you take an integer and you put it in any, you can add it to another integer. It's just that the compiler, whenever it sees an any being added to something, has to call a runtime support routine that does all the same work at runtime that the compiler did to make sure the types are right and figure out what operation to perform. So it's a lot slower. One area of interesting optimization for us will be to do some type inference and eliminate some of those any's when we can. We do not do it currently yet. We've been focusing more on the programmers who want to... Most programmers who want really high performance also are comfortable with type systems and want to use those. So we haven't really catered to the people who don't like types but want a lot of performance yet.
Yeah, so I'm not completely familiar with Python. My capsule description of it, someone gave it to me, was isomorphic to modula 3 without the types. Maybe...
Kind of more like Perl, but turned into a sane language.
That's hard to imagine.
Rather than utterly invidious.
I think maybe both.
So, if it's possible to create cycles, which I assume there's assignment, and it is, then it's not possible to give, I think, any real heavy-duty semantics to when finalizers should happen. So I'm dubious.
Well, in the case where you have cycles, then finalizers would never get called unless you explicitly go in. It has a dead object area where objects that can't have finalizers can't be GC'd. Other
Okay.
objects that have cycles are GC'd because there's a backup garbage collection that catches those.
And their finalizers, if they have them, are eventually executed?
Objects with finalizers are never GC'd. They get put in a bin somewhere where your program would have to manually decide what to do with them.
Assuming they're so
So it's up to the finalizer to free their storage data.
I don't think, if you're going to allow general purpose object graphs and some objects are going to have finalizers, I don't think it's a good idea to distinguish between objects that can be part of such cycles and say they can't, in some static way, say they can't have finalizers. So if objects have finalizers, then I think they have to be, their unreachability has to be discovered asynchronously by an asynchronous garbage collection system, and therefore it seems to me the logic is unassailable that the finalizers have to be at least conceptually executed asynchronously in a separate thread. I've never been able to see any way around that.
I think we've got I think finalizers are an example of something that gets put into programming languages because the designer is envisioning one particular method of implementation, namely reference counting. And if you give them a good semantics, that is, like a specific definite semantics, and they couldn't have that semantics if another implementation technique were used, say garbage collection. And generally speaking, I don't like that kind of language design because it restricts the class of implementations that can be used. And for right now, for a lot of applications, garbage collection works better than reference counting. And so you're restricting the range of usability of the language. Now for Python that may not matter because Python, as I understand it, is generally used in applications where performance is not a big issue, and so the performance problems with reference counting just are not as important as having a definite semantics for finalizers. So that may be a case where for Python it makes sense, but in general I don't think that's a good design.
I think that example of what people are looking for from finalizers is overly simplistic. I think that one of the common uses is if you have some model or some object that models an external resource, and when you're disposing of the object, you want to make sure that the external resource is freed up as well. The classic example being streams or something.
There are other ways to handle that besides finalizers, though.
And that's the classic screw case of finalizers too. That's the one that you should never use.
So then the question is, I mean, you're absolutely right, that's what you want to use finalizers for, but memory is only one kind of resource, and garbage collection takes care of that. And many languages also take care of file descriptors for you, but what about other things? What should be in a language to take care of automatic resource management?
Macros.
I think what's going on here is this confusion or this conflation of memory deallocation and going out of scope. Those are two different things. People use destructors in C++ for all sorts of things, like declare a local lock object up here, then when it goes out of scope, automatically let go of the lock. There's nothing about memory deallocation in that. So you confuse those two properties and you get confused.
Right. When I was saying finalization, I was meaning in the Java sense for those uses for which you might plausibly, I'm not sure I believe it, but for example, the file descriptor closing. And I think that comment about the tying of one resource, the recycling of one resource memory to other resources is a real bad idea. I don't have any great ideas on what to do about it.
I think that this points have been made so far that going out of scope is not the same thing as becoming unreachable. And sometimes finalization should be associated with one and sometimes with the other. As to how to handle the problem of becoming unreachable in a heap allocated object that may be shared among several structures, I think the best way to do that is to have weak pointers and a mechanism that a program, through explicit program code, can use to determine which pointers are accessible only through the weak pointer table, so to speak. And then if you want to finalize those, finalize them however you want and take them out of the weak pointer table. And then the burden is not on the language implementer to guess what the intent of the programmer is. It's the burden is on the programmer to express the meaning of the program.
A lot of people, besides me, like you're saying, interpretation is bad. Maybe you want to talk a few seconds about the application where my initial response time is important versus my long-term runtime. In that case, isn't interpretation the quickest way for me to get an answer when I've got a dynamic and I don't know what's going to happen? The code just arrived and I want to get an answer now, like in a web page.
Yeah, the point I was trying to make is that the sort of compiler I was describing is so fast that the number of executions of a method it takes to amortize the cost of compiling it versus interpreting it is quite small, on the order of...
Less than one, though. I mean, if I
No, it's not less than one.
Page and I just want to look at it, I probably shouldn't compile at all.
Yeah, so it's not that interpretation is dead. It's that if, except in the case you're talking about, if you're running for a minute, you better be spending a minute fraction of your time interpretation. That cutoff is on the order of 10 executions of a method as opposed to 10,000.
So, I'd like to dive into the best thing about interpreters is that they're easy to write. So you can come up with an implementation really, really quickly and get something going and play with it. So I think that's the primary advantage for using interpreters as opposed to just-in-time compilers, is you eliminate that huge engineering effort or substantial engineering effort required to get your program going.
I have a quick history question for Will. Wasn't there a programming language that implemented your kind of thread semantics called Concurrent Pascal, one of the early concurrent languages. Didn't it have just what you were talking about?
Yeah, I unfortunately don't know concurrent Pascal, but I was in fact thinking of communicating sequential processes as the kind of thing that had the kind of model I'd like to see in languages. Unfortunately, I can't comment on concurrent Pascal. Somebody else might be able to.
I can comment on CSP. CSP is an interesting language for those. So basically, the idea here is that you've got a bunch of processes that encapsulate data and they send messages back and forth. In practice, it's unbelievably cumbersome to use because you have to be able to predict when you generate a piece of data who's going to want to consume that piece of data. And it gets really complicated. And what you find yourself doing is, you know, just drilling in communication patterns. And if anybody else wants to read that data, you've got to go change code everywhere that produces it. So it's really difficult to use in practice. Now it's great if you have very loosely coupled pieces of code. Then, you know, the focus is on keeping the pieces separate, not interfering with each other. And if you isolate everything using message passing, it works great. But in, you know, most sort of moderately coupled systems, you want to be able to get data very quickly, and more importantly, you want to be able to change the data accessing patterns of your program without having to worry about who's going to produce data and who's going to consume it.
Well, actually, the thing I was thinking about was a language where you declare objects to be concurrent, and then the compiler ensures that only those kinds of objects can interact between threads.
Yeah.
So you don't do that. I think that was the name of that language. I never used it myself either.
Yeah. No, so
But people have really designed what he's talking about, I believe.
Right. And people are continuing to design safe type systems now for more complicated languages that support that kind of behavior, which is good.
On the other hand, I think it would be a misstatement to say that that insulates you from the complexity of threads. If I remember concurrent Pascal correctly, you have the equivalent of monitors, and those constructs had blocks, which were threads, right? So you could have several threads, and they would be executing operations on these monitors, and you had all the same complexities of the monitors were implicit mutexes and condition variables, and as far as I can tell, it's isomorphic to thread programming today.
Well, the big difference, though, is that you don't get some real insanities that can happen if you have unprotected races.
Startup overhead, an interesting topic. It's got a lot to do with the user experience. A lot of people, you know, time spent while you're in sort of the steady state of a program is okay, but waiting for it to come up is not. And it ties together, I think, a lot of the topics that have come up in the panel. Microsoft Windows, for example, when it's booting up, it's doing incredibly dynamic and general things. I'm looking around, you know, what kind of hardware is on my system, and you know, what kind of software has been loaded on it. But of course, most of that's silly. You know, it's going to do the same thing over and over again every time, and just waste a lot of time making the same old decisions every time. And most of the time, when things are coming up, like when Microsoft Word is coming up, you're basically executing at the speed of your hard drive, which, you know, on a laptop is not very good at all. There's a lot of evidence that Microsoft spends a lot of time optimizing that, you know, as opposed to other things, you know, sophisticated program rearrangement to get things lined up in the right order and so on. That really seems to affect you know, real user experience much more than the traditional kinds of optimization. That's sort of galling to think about the time, and I'm an optimizer person. You know, we've spent doing things like, you know, software pipelining and whatnot, when, you know, all that really matters is how fast we can pull code from the disk and pump it into the machine.
A related issue there in curl is we spend a lot of time downloading some web page that has curl content in it. And we'd like to overlap the downloading with the displaying, so it's even slower than a hard drive. And so we have this sort of incremental evaluation model where we're taking stuff sort of asynchronously from the web and then displaying on the screen as it comes down. And so you get your first screen of output fairly quickly, and then it's continuing to process stuff after you go down. So a similar issue.
In the Java world, there's efforts to have the equivalent of shared libraries, where in one, without loss of generality, here's one kind of implementation. You have some process running that has a bunch of class files loaded in it, and when you start a new Java process, it maps those pages containing the class files it cares about into its memory, and that's a lot faster than... Sorry? Yeah, well, similar.
Yeah, this is actually how curl works too, by the way. When we compile a package, we record it in a shared place, and every applet that you load that imports it just uses that same one until it's not used anymore.
An interesting research problem in that area is let's say you went through the effort of compiling these class files, would you want to share that compiled code? Would you be losing optimization opportunities by having to compile it in such a way that it's not specific to each individual program that uses it, et cetera, et cetera? So what's the trade-off there? And that's still very active research, certainly.
I'll take 2 more questions. You and then, yeah.
3 related questions. One, closely related. Are any dynamic languages borrowing significantly from Sather? 2, should they be? And 3, could you convert Sather into a decent dynamic language just by going from static to dynamic compilation?
Can I ask you some questions about Sather?
Yeah.
Which aspects of Sather do you think would be appropriate for dynamic compilation of dynamic languages? I mean, my understanding of Sather is that it's a somewhat cleaned up version of C++ to its very first order. Is that?
No, it's an Apple variant.
Not right, but I mean, it's in a sort of general static object-oriented language kind of family, right?
Mm-hmm.
So what aspects of Sather do you think would be valuable in this context that aren't being currently realized right now?
I think the most valuable aspect and the main reason it might benefit from dynamic compilation is the parameterized typing, which is nicely done. It's very powerful, but it makes compilation very slow.
Because you have to do type checking across modules for all that stuff.
Yeah.
Yeah. So I mean, my opinion is I think this kind of generic typing is a useful thing. It's an additional safety feature that you can have. I think the way to get it is to have a variant. The way it would be useful in dynamic systems is to have load the program and run it. Have an option to do it without any of the type checking, and then have the type checking be able to be done offline if you wanted to do it. That's where I think you'd get the best of both worlds. And maybe people would always do the type check, in which case, the option goes away to load it without it.
So parameterized types were a big source of overhead for our language because you might have like an array type, and if just instantiating array of int theoretically creates 200 methods or something if you look at the whole class hierarchy everywhere. But you're only going to use 5 of them typically. So we actually had to spend a lot of time working on ways to sort of only lazily compile things as you absolutely need. But it does work if you put enough effort into it.
Okay. Thanks.
So I think we've heard from several of the speakers that program annotations are great, and that one thing we'll be seeing more of in the future is new kinds of program annotations and new ways of annotating our programs to make them more efficient. So I wanted to hear from some of you what your opinions are on what's coming soon and perhaps what should never arrive. So what annotation do you think is going to be that is the low-hanging fruit? If I could add this annotation to my dynamic language, it would improve my programs tremendously. And on the flip side, what annotations do you think are going to get bandied about but really are a terrible idea, and we should focus our attention away from them as quickly as possible?
So I guess I'll take a swing at that one. So annotations that are a bad idea. Any annotations that tie 2 pieces of the program together. Any annotations that say, for example, I'm going to produce data here and use it here, and that's the only way that this data is going to get used. I think that's problematic because it like I said, it ties your program down more than it ought to be tied down. Annotations that I think are going to be very useful if you're using threads. You really want to be able to keep your private data and your shared data separate, and I think that's a useful annotation that's going to come around. I think parameterized types are going to make it into Java really quickly, although there's people here who are much more of an expert on that topic than I am. And I'm thinking of Guy right back there. And Dave, of course, is going to know much better. So I think those are the 2 extremes. I don't know. It's hard to come up with examples of bad annotations because a bad annotation. Here's a great example of a bad annotation. A bad annotation is an annotation that's not checked, like a comment. The problem is the great thing about comments is they tell you what's going on in the code. The really bad thing about them is that they're wrong sometimes. So
annotation that can be made false somewhere else without noticing.
That's right. So that's kind of, you'd like to avoid that if at all possible in your annotation language.
So I spent the 4 years of my life before I came back to Massachusetts working out in California with the group in DEC-CIRC on program verification, which was the extended static checking project, which is now, they've continued on, they've done it, have a system released for Java, and I encourage you to check it out. I think that in the future, any invariant of your program that you would like to be checked will be expressible, and you'll have at least a fighting chance of having a program verifier statically verify that. So you'll be able to give representation invariants of your abstract types, requires clauses of your calls, specify locking orders so you can prove absence of deadlock, specify, these fields of this object are protected by this lock, and verify that that lock is held whenever those fields are accessed, etc., etc. I think, I hope, because it's the only way we're going to really make correct software, that becomes true in the future, that this is just a matter of course, that your program doesn't work until the verifier says it does.
I'll give you an easy to implement one that we borrowed from Dylan. Dylan has this concept of sealing classes, which means that you can't subclass the class outside of its module. That's really useful for optimization because you can turn procedure calls into method calls because you can see that the method can't be overridden outside. It's very, very cheap to implement, and it has proven a big win.
All right, let's thank our wizards.
Well, guys, it was fun, huh?
Yeah.